Hi, Richard.
Hello.
Yeah. So we wrote this book, and it was based sort of around the idea of family trees and that sort of thing. And I guess most people are sort of used to the idea of a family tree, but what's happening at the DNA level is, I guess, the realm of biologists.
Well, yes, and I think that was a thing that we really came up with and explored in a big way, was the distinction between counting family trees at an individual body level. You know, you've got 4 grandparents and 8 great-grandparents and 16 great-great-grandparents and so on, until they start overlapping, and which they will, they've got to. But you could also do the same thing for every gene in your body. Every gene in your body can trace its own family tree back and has an origin at some point, and that origin has a number of descendants. Not all human.
Yeah.
It's a very wonderful idea.
Yeah,
actually. The lovely idea that each gene has its own idea of the family tree. And from many points of view, you and I are quite distant cousins, but from certain points of view, from the point of view of certain genes, we're probably very close cousins, and not very close, but I mean closer.
Yeah, closer, exactly.
With respect to that particular gene.
Yeah, or section of DNA, I
guess.
And I guess one of the interesting things is that while the family tree, as you go backwards, your genealogy, your family tree sort of expands, the one of any one particular gene starts sort of contracts down into individual lineages. And this is what this picture we had in the book sort of represented, in that these were the great-grandchildren.
So there's Albert and Victoria there.
Right. Yeah.
And these must be all the other ancestors of Albert and Victoria's descendants. And this line traces the haemophilia gene. Yeah. Some of whom were female and therefore didn't actually have haemophilia. Some of whom were male who did.
So this is, if you like, the black is the family tree, and the red is just tracing one gene tree, and it goes back and back and back and contracts in time until it comes back to one.
Yes.
And you can do that with presumably any gene.
You could do it with any gene. I mean, haemophilia is easily labelled, easily marked. You know who had haemophilia. These poor guys all died of it probably. And so that's just a tracer marker. Yeah. And you could have done that with any of your genes. It would make a similar pattern.
And this is the thing. This is effectively what we're doing with mitochondrial Eve.
Yes.
But you're just tracing the female line. It's a specific line, but it still sort of contracts
The problem with sex is that it constantly mixes up all the genes, and so tracing back would be just a mess. Since the mitochondria only go down the maternal line, you can forget about all your grandparents except one, your maternal grandmother, all your great-grandparents except one, your maternal great-grandmother, etc. So in every generation there may be 16 great-great-grandparents, but only one of them gave you your mitochondria, and so you can trace your mitochondria much more easily, and that's why geneticists use mitochondrial DNA as their preferred marker.
I guess the problem with that is that, of course, with the great-grandparent generation, you might have you're sort of representing one thing in 16, and as you go back, it just gets multiplicatively worse and worse. So you're representing a smaller fraction of your ancestors.
That's if you care about. Yes, I mean there was a rather deplorable television program. It was not a BBC one, I think, in which the conceit of the program was to gather some, I think, two or three people, and trace their mitochondria, and traced it back to, as it happened, I think, West Central Africa. And you saw this woman going back, my people, my people. Of course, it was nothing of the kind. It was just where her mitochondria came from. Her other genes would have come from all over the world.
So it was one of her people, but then there would have been thousands of others all over the place.
Yes,
I guess.
Yes, millions.
And that's, I think, the problem I have with using mitochondrial DNA. It's very informative, trying to trace back in time like that using mitochondria, but it only gives you a tiny picture of what's going on with the whole of humanity. So drawing deductions from just one gene is...
Yes, that of course is true, but it does enable you to put dates on certain... I mean, mitochondrial Eve, so-called, is just the most recent common ancestor in the female line. We've got lots of other common ancestors in all sorts of other lines, and mitochondrial Eve is almost certainly not the most recent common ancestor, because there are so many other ways in which you could trace the ancestry, taking other genes. So this is the most recent, taking just one.
And as we said, that you'd only go back to a few thousand years or something probably before you hit the most recent one.
Yes.
That sort of.
Whereas mitochondrial Eve would be what 100,000 years or something like that?
Between 200,000 and 100,000
Yes.
is the current
Yes.
sort of guess.
Yes.
I'm not convinced about using the names myself.
No.
I don't know if you are. Do you think
Well,
people are misled by it?
Yes, they are, because they kind of get the idea that mitochondrial Eve was awfully lonely.
Yes.
Of course she wasn't. She was surrounded by companions, many of whom are also our ancestors. And indeed, 80% of them, or have I got that right? Yes.
Yes, I
Yes.
guess so.
But she's just the most recent common ancestor in this particular female line. So calling her Eve could be misleading in that people might think she was all alone.
And indeed that she was a particular person, because it's a sort of honorific title.
Well, it's an honorific title in the sense that if, say, the population of Tasmania, the Aboriginal population of Tasmania were to go extinct tomorrow, then we would no longer have to reckon on the ancestor of the Tasmanians. And so the title of mitochondria, rather like the title of the Duke of Dunstable. The title mitochondrial Eve would then leap forward maybe 10,000 years, as if you get rid of a certain subpopulation.
I guess it sort of depends on basically which group of humans you choose to include in your calculation. Because we could find a mitochondrial Eve between me, you, and the rest of Oxford, and it would trace back to one person.
That's right.
And we could call her Eve, but then you think, maybe we should include the rest of humanity too.
Yes.
But then if some other people die, then it just might change to a completely different person.
Yes, exactly. And it's normally conventionally used to mean the mitochondrial Eve of everybody in the world. But if everybody in the world changes, some people die, some major group dies, then the honorific title shifts. And the other one that's easily traceable is the Y chromosome, because just as the mitochondria go down the female line, the Y chromosome goes down the male line.
I think there's a little bit of a misleading thing there, because people think that the mitochondria cover the female side and the Y chromosome cover the male side, and between them that covers everything. But of course that's not true at all, because they only cover that one line back straight.
That's right. Yeah. But it is interesting to ask whether Y chromosome Adam ever met mitochondrial Eve, and the answer is absolutely, almost certainly not.
And also because males have a much bigger variance in reproductive success. Some of them have hardly any offspring, and some of them have loads, and that means that their family trees collapse to a point much more quickly.
How many offspring did Moulay Ishmael the Bloodthirsty have?
I don't know.
More than 800 anyway. So the chances are pretty good that we're descended from him.
Yeah, well, that's
and
true.
Genghis Khan
as well.
Khan. Yeah, there's actually evidence that, looking at Y chromosomes, that some enormous number of the population of Central Asia are descended from one male at about the time of Genghis Khan.
I mean, it's my paternal side that's Chinese, so hopefully I might well be able to.
Well, you hope that you inherit some of his.
Well, more for intellectual interest than anything else. I think what's also interesting is that some of the recent research that people have done on Neanderthals and sort of getting whole genome sequences out of fossils has sort of confirmed what we were saying, because there was this argument, wasn't there, about Neanderthals, whether or not they interbred with humans.
I mean, obviously, if you go back far enough, then Neanderthals and us have a common ancestor anyway. But the issue is, once they've diverged quite a long way, then could there have been a little trickle of interbreeding a bit later? And the evidence from the Neanderthal Genome Project is yes. Only in Europeans, though.
And what I find really interesting, actually, is that before we had the entire nuclear sequence from the Neanderthals, people were just relying on the mitochondrial sequence, and they thought that Neanderthals weren't at all related to humans because their mitochondrial sequence is way off from all the rest of humanity. But now we've got the full nuclear sequence, it does look like there was some interbreeding. So it is really very much that idea of, I guess, your sort of idea of the selfish gene, that you look at the genes in turn, as it were, or the sections of DNA that have independent histories in turn, and they different things have happened to them.
I think it's a wonderful vindication of the idea of the selfish gene.
Yeah. Well, but thank you very much, Richard.
It's been a really pleasure as ever, Jan. Thank you.
The more questions you answer, the more you find there is to investigate.